Hello everyone, welcome to this lecture in the Neural Networks from Scratch series. This is a set of lectures on backpropagation. Up till now, we have covered backpropagating through layers and finding the gradient of the loss function with respect to the weights and biases of layers. And in the last lecture, we also looked at backpropagating through the ReLU activation function. In this lecture, we are going to look at backpropagating with respect to the loss function, which comes towards the end of the neural network. So, if you look at a neural network architecture, it looks something like this, where there are inputs, then it goes through a set of layers, and then there are outputs. I am considering a classification problem here. Um, so what will happen is that here are three output neurons. They go through a softmax activation function, and then the output from the softmax is denoted by y hat 1 1, y hat 1 2, and y hat 1 3. The second index 1, 2, and 3 describes the position of the neuron. So this is the first neuron, second neuron, and third neuron. And the first index, which is 1 in all these cases, represents the batch of the input data. So here the input, let's say, is x1, x2, and x3. This is the first batch of data, right? But there can be 100 such batches. That's why that's the first input or the first index right here. So when we do back propagation, let's say we want to find the derivative of the loss with respect to either of the weights in the layers or the inputs of layers, the first thing we need to find is the derivative of the loss with respect to these outputs. So that's what we are going to look at in today's lecture. Initially, let me tell you a bit about how the loss is calculated in this case. So we have a classification problem here. So the loss which we are going to use is called as the categorical cross entropy loss. I have a separate lecture on this in the machine learning teach by doing series. So if you are not aware of this loss, please go to that lecture. I'll explain this loss briefly here itself. So in this loss, what we do is that if the predicted outputs from the softmax are y11 hat, y12 hat, and y13 hat, and the true output is y11, y12, and y13, then the loss function is usually given as negative of y11 into log of y hat of 11 plus y12 into log of y hat of 12 plus y13 into log of y hat of 13. This is called as the categorical cross entropy loss. Now, usually, since this is a classification problem, let's say for these set of inputs, the true class is the first class. So the true labels will look something like this. Y11 might be equal to 1, Y12 will be equal to 0, and Y13 will also be equal to 0. Usually, this is how the true labels look like in classification tasks. Only one true label will be equal to 1, the others will be 0. So when you find the loss function and calculate it like this, y12 is equal to 0 and y13 is equal to 0. So these terms won't matter. The only term which will matter is the first term. However, for the sake of calculation of this derivative, it's much more useful for us to write down these entire set of equations like this. An intuitive way to think about the categorical cross entropy loss is that if y11 hat is close to 1, if y11 hat is actually close to 1, which means that we are doing a very good job, right? Our loss should be 0 in this case. This is exactly what happens. If you put y11 hat equal to 1, log of 1 will be equal to 0, and then the loss will be equal to 0. On the other hand, if y11 hat is, let's say, equal to zero point 0.1, then log of zero point 0.1 will be a high negative value. So if you take negative of that, it will be a high positive value and the loss would be even higher. That's the intuition behind the categorical cross entropy loss. Now, what we need to do is that if you want to find the partial derivative of L1, which is this loss over here, with respect to, let's say, this weight in the first layer, W11, we will do back propagation right from here to the first weight, right? So the first term of this back propagation will be partial derivative of L1 with respect to um, y11 hat, and then we will multiply this by a number of other terms. But the first term of the back propagation will always be the partial derivative of the loss with respect to the predicted outputs. So that's what we will calculate in today's lecture. So first I'm just going to show you a simple manual calculation. Then I'm going to show you how to do this with matrices, because we'll be using a batch of data, and then we'll be jumping into code. So that's how this lecture will be divided into three parts. Let's get started with the first part, where I'll show you how to manually find the partial derivative of the loss one with respect to y11 hat. So let's look at the loss one and its mathematical representation. So loss 1 or L1 is given by negative of y11 into log of y11 hat plus y12 into log of y12 hat plus y13 into log of y13 hat, and we want to find the partial derivative of L1 with respect to y11 hat first. Okay, so first you can see that this term and this term do not have y11 hat, so their partial derivative with respect to y11 hat will be 0. The only term which will survive is the first term. Y11 will be a constant, and the derivative of a log is 1 by, so if you have y is equal to log of x, then the derivative of this is, or y dash, is actually equal to 1 by x. So the partial derivative of log of y11 hat with respect to y11 hat would be 1 by y11 hat. So when you take the partial derivative of L1 with respect to y11 hat, the answer will be negative of y11 divided by y hat of 11. So essentially it will be negative of the true value divided by the predicted value. Similarly, when we take the partial derivative of L1 with respect to y12 hat, we will only look at the second term here, and then this will be minus y12 divided by y12 hat. So again it will be true divided by predicted and with a negative sign. Similarly, when we take the partial derivative of L1 with respect to y13 hat, the answer will be negative of y13 divided by y13 hat. So again that would be the true uh, divided by the predicted. So if you were to represent this in vector formulation, what you will do is that you will first take the so it generally seems that we are looking at negative of true versus the predicted, right? So this can even be written in vectorized formula. So what is the true vector? So if the true answer is 1, 0 and 0, so then this vector will be negative of 1, 0 and 0 divided by my prediction. And if the prediction is equal to zero point 0.7, zero point 0.2 and zero point 0.1, so you will do a broadcasting here. So in Python, when you do broadcasting, the first term of the numerator is divided by the first term of the denominator, and this happens for all of these three. So then the answer here would be negative of 1 divided by zero point 0.7, 0 and 0. And this answer will then be propagated backwards. After calculating the partial derivative of loss with respect to these outputs, then we can go backwards and find the partial derivative of loss with respect to the weights and biases in the preceding layers. So if we have a categorical cross entropy loss, finding the partial derivative of loss with respect to the outputs is as simple as taking the negative of the true predict or the true value divided by the predicted value. Now I want to show you how to do this same thing if we have a batch of data. It's actually very simple. If you have a batch of data, then the then this calculation would look like this term would be replaced with a matrix, and this term will also be replaced with a matrix. And then you will take the division of the first element of the first row with the first element of the second row, etc. So let me show you how that would actually look like. So if you have a batch of three input data, so if you have a batch of three input data, so let's say then the true values are 1, 0, 1, 0, 0, 0, 1, 0, and 0, 0, 1. Then this will be divided by my prediction values. So if the prediction is zero point 0.7, 0.2, 0.1, and let's say this is also zero point 0.6, 0.4, 0, and let's say this is 0, 0, and 1. So then you will be taking the division of each term of the numerator with each term of the denominator. So remember, this is a batch of data. So this is the first input batch. So for the first set of data, for the first set of x1, x2, and x3, the output is 1, 0, and 0, which means the true class is the first one. For the second class of data, the output is 0, 1, and 0. So this is the second class of data. So for the second class of data, the output is 0, 1, and 0, which means the correct answer is the second, uh, or for the second input of data, the correct answer is the second class. And for the third input of data, the correct answer is the third class. So that is the input. And for each of this input data, we will get predictions from these three output neurons. And those predictions have actually been represented over here. So for the first input data, the prediction is zero point 0.7, zero point 0.2, zero point 0.1. For the second input data, the prediction is zero point 0.6, zero point 0.40. And for the third input data, the prediction is 0, 0, 1. So the result will be that we will just divide the first row, first column of the numerator with the first row, first column of the denominator, etc. So actually the answer would be, in the first row, so this will be a negative sign. In the first row, the term which will survive is 1 divided by zero point 0.7, and all other terms are anyway 0. So I am going to write 0 and 0. In the second term, what will survive is 0, and then 1 divided by zero point 0.4, 1 divided by zero point 0.4, and then this will be 0. And in the third term, it will be 0, 0, and 1 divided by 1. So the answer will be 1. So this will be the derivatives. Remember that this is a matrix which is a 3 by 3 matrix. So it's 3 rows and it is 3 columns. So the first row here represents the partial derivative of the loss with respect to the first input data. The second row here represents the partial derivative of the loss with respect to the second input data. And the third row here represents the partial derivative of loss with respect to third input data. So this negative of true versus prediction, what I showed you, can even be extended for a batch of input data, as we just saw in these calculations. Now, I just want to show you a mathematical notation. You can feel free to skip this particular part. Uh, so whatever I just showed you manually here, I will just write it now in mathematical notation just for the sake of completeness. So the loss with respect to the ith batch, so I denotes the batch or the sample. So L1 means the first batch of data, can be written as sigma yij multiplied by log of y hat ij. So why do we have two labels here, I and J? I corresponds to the batch. So here see Y11. One means the first batch and the second index means which neuron is it. So I corresponds to the batch and J corresponds to which neuron it is. And then the partial derivative of Lij with respect to, or Li with respect to Y hat, is just negative of the ground truth divided by the vector of predicted values. So this is exactly what we did. We take the ground truth vector, which in this case was 1 0 0. We take the negative of it and then we divide it with the vector of the predicted values. So this was the mathematical representation of what I just showed you on the whiteboard. And now we will code this in Python. So the reason we need to code this is that we have already defined the forward pass with respect to the loss, and I'll be sharing this notebook with you. So if you scroll up in this notebook, you will see that yeah, we have implemented the categorical cross entropy loss, and in this class we have defined a method called forward. But now we will also be defining a method which is called backward in this class, which will take the derivatives of the loss with respect to the outputs of the previous layer. And I already showed you manually how to find these derivatives. It is just the negative of the ground truth vector divided by the vector of the predicted values. But now I want to show you how to represent it in code. Okay. So if these are the uh, predicted values, so if this is the predicted values, you will see that there are three batches here. The first row are the predicted values for the first batch. And remember, there are four neurons here. This is the output of the first neuron, second neuron, third neuron, and fourth neuron for the first batch of data. This second row is the second batch of data, and the third row is the third batch of data. So the number of samples which we have is equal to 3, and the number of labels are 4, because for each sample we have 4 neurons in the output layer. So these are called D values because they are the output values, and we'll calculate the loss based on these. Correct? Now, let's say if your true values are these 1, 2, and 3, which means for the first input batch, the correct answer is 1. For the second input batch, the correct answer is 2. And for the third input batch, the correct answer is 3. Now, the problem is that if the correct answers were in the form of vectors, you can just divide the true value with the predicted value, right? And take the negative of that division, like what we saw over here. But what if the true values were not in the form of vectors, but they were in the format of numbers? If this is the case, then what we will have to do is we will have to use a technique which is actually called um, one hot. This technique is called one hot encoding. So what one hot encoding actually does is that it will create, or it will convert these set of numerical values into vectors. But how to do that? We'll need two things for this. We will need so if you look at the samples will just be equal to the length of these D values. So there are three samples here, so that will be equal to 3. And to find the number of labels, what we can do is that we can look at the first row and then just count the length of it. So the first row is D values indexed by 0, and then the length of it is equal to 4. So then to do the one hot encoding of this, we use a numpy notation called np.i. So np.i and then 4. So 4 is the number of labels because there are 4 labels. And then we put y true. What this will actually do is that it will take each element of y true and convert it into one hot encoding with 4 labels. So the first value is 1, right? So it will be 0 1 0 0. The second value is 2, so it will be 0 0 1 0. The third value is 3, so it will be 0 0 0 and 1. So this is the np.i command in Python. You can even search the np.i or numpy.i documentation, and then you can see that it takes in the first argument, which is the number, and then it creates the one hot encoding based on the number of labels. So in this particular case, what we have is that we have put 4 as the number of labels. So what it will do is that it will take each element of y true, and based on these number of labels, it will convert it into the one hot encoded format. So what we'll do next is that once y true is in the format of a matrix, then we can actually do this division very easily. So then we will just do negative of y true divided by the d values, which is very similar to what we have done over here. We'll just do the division in a broadcasted manner. So once we actually do this negative y true divided by d values, it will be taking the division of the d values matrix with the y true matrix who have the same size. So Python will perform broadcasting where each element of the first matrix will be divided by each element of the second matrix, and we'll get this particular answer over here, this matrix. In the actual code, we won't stop here, but we will normalize every single element of this matrix with the number of samples. The reason we perform normalization as the last step is when we do gradient descent later, we will actually add the gradients for every single sample. So if you don't do the normalization, then the derivatives may blow up to a huge value, and we do not want to do that because it makes convergence very difficult. So if we divide by the number of samples, then the gradients actually stay in between 0 and 1. And even if we add it by the number of sample times, then it will still not be a very large value. So normalization actually ensures this, and that's why we normalize by the number of samples towards the end. Okay, so this is the final output which we have, and I've demonstrated this to you manually. Now I'll show you how this is implemented in code format. So this is the categorical cross entropy loss class, and I already showed you that we have implemented a forward pass. Now we'll be implementing the backward pass here. So we'll be defining the backward method, and it takes in two arguments. It takes in d values as the first argument, which are the predicted values, and it takes y true as the second argument, which are the true values. So as I demonstrated over here, we will need two numbers, the number of samples, which is the length of the d values, and we will need number of labels, which is the length of the first row of the d values. So this is just implemented in code over here. Samples is the length of d values, and labels is the length of the first row of d values. Now if the y true is a set of numbers, so if the y true is a set of numbers like it was over here, we need to convert it into a one hot encoded format. One way to check whether y true is a set of numbers is to check the shape of this, and then to check the length of the shape. So if the length of the shape of y true is equal to 1, it means that y true is just equal to numbers. Then we will convert it into a one hot encoded format using the np.i command which we just saw. If the length of y true dot shape is 2, it means that it's already in a vectorized format, or it's already a matrix. So we don't need to convert it into a one hot encoded format. And then we just take the gradient, or we calculate the gradient, which is just the negative of y true divided by d values. So this will be a broadcasting operation where each element of y true will be divided by the corresponding element of d values, and the size of this resulting matrix will be exact same as the size of y true and d values. As I told before, we won't be stopping here. We will be doing a normalization step where every single element of this d inputs, which is the output which we want, is divided by the number of samples. This is to prevent gradients from accumulating to large values when we are doing the gradient descent. So that's it. This is the back propagation or the backward method implemented for the categorical cross entropy loss. Once you understand how it is written on the whiteboard, then implementing it in Python is much more simpler. This actually brings us to the end of today's lecture. We covered a lot of things, including taking the partial derivative of the loss with respect to these outputs. Um, in the next lecture, I will show you how to implement the backward uh, pass, or how to implement the backward method in the softmax activation class. So up till now I showed you how to find the derivative of loss with respect to the outputs, right? But there is a softmax function which happens before. So we will need to find the derivative of the output of the softmax with respect to the input of the softmax, and that will be used to calculate the previous derivatives. So just this one more step is remaining in backpropagation, and then I'll show you how to chain all of it together. We have developed all the building blocks. In the previous lecture we have calculated the partial derivative of loss with respect to weights of layers and inputs of layers. We have also calculated the partial derivative of loss with respect to ReLU activation class, and in today's lecture we found the partial derivative of the loss with respect to the output values. The only thing which is remaining is now to find the partial derivative of the softmax output with the softmax input, so that we can use it to complete our backpropagation chain. Uh, and I'll demonstrate that to you in the next lectures. So thank you so much everyone for sticking with me up till now. I don't think there is any other course which explains backpropagation in so much depth. And I deliberately wanted to show you this because the title of this playlist is Neural Network from Scratch. So I'm not assuming anything and I'm showing everything to you from scratch. I hope this adds value to your machine learning journey. Thank you so much everyone, and I'll see you in the next lecture.